Lord, dang it, Gabriel's here. Kaylin's here. Just need Alex. One more. No? All right, I guess we'll have to get started without him. Then good morning, everybody. I hope you have enjoyed our factoring so far. It's one of those pleasant moments in math where you get into the groove of it and it just kind of works itself out, and it's very satisfying when you can rearrange those equations into their nice factored form. So we're going to start today with, I'll show you the answers for yesterday's worksheet. You can check those. I'll answer questions about them. I imagine you're going to ask about the word problems the most, but if we have to stop for anything else, we can. And then the rest of the day will be a new technique for solving some factored equations. All right? So without further ado, here is, for anyone that missed number 9, since I went back and did this after the live stream, there it is. I posted an image back on Google Classroom. It turns out I did, in fact, have it correct, the process anyway. I just screwed up this sign here, which then threw me off. It's like, wait, but this is plus and that's minus, and so I wrote it down wrong when I got to there, and that's what threw me off. But otherwise, yeah, very possible. And now you have factored out the C plus 1 as the GCF, and this is another difference of squares, so you separate that out and you get your final result. Okay, but onward to the rest of yesterday's sheet, which is here. All right, Alex has made it. Excellent. There we go. Thank you for the update. I'm just going to scroll through here. Nice and easy. Stop me at any point if you need anything. And if you watched the class video yesterday, you would know you got to skip those division ones at the end. We'll come back to dividing polynomials sometime next week. Or possibly the week after. I'll have to double check. But we'll get to it. We'll get to it. Don't worry about those now. All right, last call for questions on the first page. No? All right, excellent. Well done. Here is the second page. Things got a little bit more complex, some of them. They seem to have thrown more of these double letter ones at you. And once again, skipping the division questions. Any questions so far before we hit the word problems? 21. I figured that was coming. Yeah, 21 and 22 are probably the worst ones on here. Let's take a look, see what we can do with 21. Okay. Ooh, a lot going on here. Let me switch to another pen so you can see my work versus the final answer. And we'll go blue laser too. So this is a 5. This ends in a 5. I'm going to guess 135 is divisible by 5. I don't know that one off the top of my head. Good old calculator app, where are you? 135 divided by 5. That's 27. Okay, interesting number to work with. So we can at least pull out the 5, and we'd be left with just some y's plus 27. And of course, we can pull out the y squared, so that leaves it with only 27 at the end. And this will be y cubed up there. And this is where things get interesting, because 27 itself is a cubic number. 3 times 3 times 3 is 27, which means this guy, move those out of the way, is a sum of cubes, right? And that was the equation. Did it still have that on the front page here? Sum of 2 cubes, there it is. All right, so we're going to take, this is what we have, except instead of a and b, we have y and 3. Okay, so we're just going to repeat this format down there, replacing a with y and b with a 3. And that will get us right to the final answer. Sum and differences of cubes do not come up often enough that I ever bothered committing them to memory. You can, if you so choose. You might find it worth doing. I'm not going to put them on my test this year, so if that's what you're concerned about, don't worry about it. But it is something you can have in your notes, so even if I did, you can look that one up, right? It's one of those very common formulas that's like useful but not good enough to memorize, so everybody has it on their note card ready to go. Okay, so that's something you'll just check. Oh, I recognize that it's a thing to then look up and check real quick. So you look up that formula and you write it out. One of each added together, and then it's the quadratic left over. Swap the first sign, keep the second, right? Square versions of both, product of the 2 in the middle. It's not a bad pattern to work with. That's all 21 is. Not actually too bad. All right, 22 is similar. This is a gigantic nesting difference of cubes, or not difference of, difference of squares. You'll do a difference of squares once, and you'll get 9x squared plus 4 and 9x squared minus 4, but then 9x squared minus 4 is itself a difference of squares, so you can split that yet again. Okay, any other questions up here? Then let's take a look at the word problems. Number 26, Bobby Joe is using a software package to create a drawing of a cross-section of a brace as shown at the right. So this is some little metal piece that you stick in the corner to hold up your shelf, right? Write a simplified factored expression that represents the area of the cross-section of the brace. Okay, cross-section of the brace, cross-section of the brace. There's no real interpretation here as far as the real-world context. Here's a picture, represent the area of the picture. Okay, so we've got a rectangle and another rectangle. They give you this suggested dashed line right there. So This rectangle being 8.2 wide and x high, we're looking at 8.2 times x. And then this other rectangle attached to it would be, well, we can't go all the way to 12. It's this much short, which is x short. So it's 12 minus x short times x. So that would be the area of this guy, and then you need to add them both together. So add those together. Go ahead and distribute that, add them up, combine like terms, then refactor it back out, and you will be left with x times 20.2 minus x. And yes, it is very likely you'll end up with a word problem or two on our next test. The next one, 27. I hope you remember your circles from geometry. In an internal combustion engine, the up and down motion of the pistons is converted into the rotary motion of the crankshaft, which drives the flywheel. Okay, a lot of extra information, doesn't really give us much here. Let R1 represent the radius of the flywheel at right. So they've got it drawn in. It's the radius of the big wheel there. Let R2 represent the radius of the crankshaft passing through it, so the diameter of the rod through the gear there. They call it a flywheel, but it is some sort of gear or sprocket there. If the formula for the area of a circle is area equals pi r squared, oh, you didn't even have to remember that. They gave it to you. Write a simplified factored expression for the area of the cross-section of the flywheel outside the crankshaft. Okay, outside. So they are asking for the area of a donut here, an annulus. They want everything out here but minus the bit in the middle, right? So we want the big circle, area 1 equals pi r1 squared, area 2 equals pi r2 squared, and we're going to subtract the 2, right? a1 minus a2, that's it. All right, factor out the pi. Okay, so you'll get pi out of r1 squared minus r2 squared. Hey, it's a difference of squares, except it's a difference of, so a difference of circles is a difference of squares. How's that for a tongue twister, right? Or brain bender there. So you separate them out, difference and sum. Right, any remaining questions there? Then let's take a look at our work for today. Solving using quadratic techniques. Turns out quadratic equations are pretty nice because we have a lot of good factoring tools to work with, but when in doubt, you can of course always rely on the good old quadratic formula. Works every time, solves all your problems, right? But not every polynomial is, of course, a quadratic, except, secretly, some of them are quadratics in disguise. We can rewrite them as a quadratic using the most magical of calculus tools, U-Substitution. Why did they call it U-Substitution? Well, it's quite simple. We're going to use the letter U to replace some power of our original variable. So instead of this being an equation on A and a 6th degree polynomial, we're going to let U equal A cubed, because we know that a squared is just a cubed, or sorry, a to the sixth is a cubed squared, right, as they show here. And so when you rewrite this, I'm going to go one step further and make it nice and clear. This is 3u squared minus 9u plus 12. Oh, now it's a regular old quadratic. This is much easier to deal with. I can use all my standard quadratic techniques. We can GCF out that 3. I guess we could have done that before too. But this one won't actually factor any further. I did test this beforehand, that those darn signs are in the wrong place. Otherwise, we could just factor it. But you can just go through, use your quadratic formula here. And you do that and you get some answer, right? U is equal to positive, negative, right? B plus or minus square root, all that good stuff. Whatever it ends up being, okay? Then go back one more step, un-U-substitute, and go back to, that means that's a cubed is whatever that answer was. Right. And now you have a much simpler equation to solve that way. Right? Again, why did they pick you? I don't know. Probably somebody was thinking you was funny, like, I can't solve this, but you can solve it. Math pun, it's terrible. I'll be here all day. Anyways, so what we're going to practice doing on the first page here is just the U-substitution part. No actual solving required. In fact, forget this extra bit at the end for now, for the first page. Look at example B here. We've got b to the linear power minus the square root of b. Hey, wait a minute. Okay, square root of b is b to the 1/2 power. You recall your exponent rules. So we're going to let that be our u, so that now this regular b is 1/2 power squared, you see. So this now becomes a u squared, just a u term, and then our constant. Right? Again, this is 101 u squared minus 49 u plus 42. You could solve that if you had to, right? Now it's a quadratic. It's easy. This one, however, you can't do because it's an odd power, right? There is no simple power that turns something squared into 5, right? It's going to make things more complicated. So U-substitution in this context is good for, you need a even power, okay, or a 1/2 power, and you're also looking for a trinomial or binomial, right? Because obviously, if I started with, even if this was a to the 6th, well, if I also had an a to the 4th and an a to the 5th term there, I couldn't swap all of those out. In fact, if you have a trinomial, your second term, even better, like we need an even power, we need a trinomial or binomial, and even more specifically, one power is 1/2 of the other. Okay? This example only works because this is a to the 3rd is half of 6. 3 is half of 6. It works. I can use U-substitution. I can represent this as a quadratic expression and then solve that. So on this first page, you're just going to write it into quadratic form where possible. Okay? It sounds like pretty restrictive, and it can be. But when you don't have any other tool, this kind of, it expands our scope of problems that we can solve algebraically a little bit. It doesn't solve every problem, but it does grow the field, as it were. So just practice the rewrites there. And then on the second page, which is fewer, there's only 12 of those, you will then go ahead and actually solve them, right? So once again, take your original equation, 1, 2, 3 terms, trinomial, x to the 4th, even power, check. The other term, x squared, this is half of the other one, check. It meets all my criteria. I can work with this. In this case, we are going to find that lower half. We're going to say, let that be our u, and this should become u squared. You do that substitution. It's now u squared minus 40u plus 144. Hey, we can factor that guy, in fact. Right? Factors of 144 that add to negative 40 are negative 4 and negative 36. Totally works. So you might get lucky, and you can even use your factoring tools here. Now, of course, this one is a little tricky in and of itself because both of these happen to be now difference of squares. So x squared minus 4, you get minus 2 and positive 2. And then minus 36, so you get positive 6 and negative 6. All 4 answers are our original answers, and that checks out with our rule for polynomial. We know that this is a 4th degree polynomial. It should have at most, it does have 4 roots, some of which may or may not be real. So in this case, all 4 of them are real roots. Positive negative 2, positive negative 6, done. Okay. And same thing with the square root. This is half of the 1 power, so we're actually going to make that be our u, and this becomes u squared, so single x becomes u squared. They are rewriting what u is equal to in parentheses for these examples. I personally would just go ahead and treat it much like up here. Write this down, u is equal to a cubed. And then I would just write u in that place each time because it's clearer for me, and just deal with that one step at a time. Then at the end, so if I go back to this guy, I would have u here, u minus 4, u minus 36. Okay, ZPP, either u minus 4 equals 0 or u minus 36 equals 0. And you can use the square root property, right? You can solve and say, oh, okay, so u is equal to 4. You can get down to u equals, then swap back. X squared equals 4. Ah, okay, so now I just square root, right? Because it's a square root number. Okay, so both methods will take you the same place. Just do watch out for that positive negative thing. Don't ever ignore a negative square root. Right, you got to have that positive negative. All right, any questions on that process there? Just the 12 here, yep. All right, then I will leave the rest to you. We've got, how much longer? 10, 14, 15, almost 20 minutes to work. Go for it. You could probably finish the first page with that. Just the substituting part, almost very little computation involved on that first page there. That should go fairly quickly. I'll leave it to it. Which pages? The whole thing. This 7.3 solving using quadratics worksheets. That is the whole thing. There's only the 2 pages. My program here automatically adds an extra blank page onto the end things in case I need more room to write. So that's why it looks like there's 3. Okay.